Bismillahirrahmanirrahim. Assalamu alaikum everyone. In this lecture we are going to discuss the Lie symmetries of nth order linear ODEs. We will show in this lecture that the nth order linear ODEs admit at most n Lie symmetries. At least, not at most, at least n Lie symmetries. So let's start. We have an nth order differential equation. You see, nth order differential equation can be written in this way: an of x yn a n minus 1 of x yn minus 1 up to a1 of x y dash plus a naught of x y, and that is equal to some function of x. So this is a nth order linear non-homogeneous ODE. So this ODE1 admit there are the solution of equation 1 takes the form y, that is the solution, yp and yc. So yp is the particular function and yc is the complementary function. So what is yc? Yc, so the symmetry lies in this yc. So I'm explaining the yc. Yc, there are this is the solution. Okay, yc is the solution of the homogeneous part, that is yc satisfy the equation yn yn, all of them are function of x, so I'm not writing all. N minus 1 of x yn minus 1 and up to a naught of x y, and that is equal to 0. So this yc satisfy this equation. So this is the solution of the homogeneous nth order linear homogeneous equation, and it can be written in this way: c1 y1 c2 y2 cn yn, where y1 to yn is the fundamental set of solution of equation 2. Okay, so this is the superposition of all the fundamental set of solution and it satisfy equation 2. Now I can write this in a simple way. YC is equal to CI YI, and there is a samana I, and I goes from 1 to n. Okay. So we take a transformation. Let's see. Take a transformation y, capital Y, which is small y plus epsilon in YC. It can be written as y plus epsilon C I Y I, and I claim that it is a symmetry, Lie symmetry transformation. Okay, if it is a Lie symmetry transformation, then it will satisfy equation 2. And you see, equation 2 can be written. Let's put it in the equation 2. Equation 2 is a n y n plus a n minus 1 y n minus 1 up to a naught y equal to 0. So my claim is that the capital Y will satisfy this equation, that is a n capital Y n a n minus 1 capital Y n minus 1 up to a naught capital Y equal to 0. It satisfies. So let's put it in the next slide in this equation. So what is capital Y? Capital Y is small y plus epsilon Ci Yi plus an, there is nth derivative yi, this is n minus 1 y plus epsilon Ci Yi n minus 1. This is not power, it is derivative. And let's write the last term, a naught y plus C I y I, and it must be 0. We can split it into a 0 y and collect all a n y n a n minus 1 y n minus 1 up to a naught y plus epsilon, and let's take Ci also common, Ci it is a derivative, so you can take it ci common because it's not a powers, it only hit the yi everywhere. So that is y I n y I a's are there. This is a n. So let me write this again. Plus up to this term epsilon ci. So they both are constant. I take it out. A n y I n a n minus 1 y I n minus 1 n up to a naught yi, and that's it. So as y is the solution, so this whole part is 0. Also we have this yi's are solution, so this is also 0. So what it is? This is in fact capital Y, capital Yn, a n minus 1, capital Y n minus 1 up to a naught capital Y, and that is equal to this 0 and plus epsilon ci and 0, and it is 0. So that implies y capital Y, which is the transformation small y, plus epsilon ciyi, where I goes from 1 to n, is again a solution. So this transformation solution. So this transformation y plus epsilon ci yi is Lie symmetry transformation, and we always define eta. So let define eta, so that will be eta I, because here is the I index. So partial y, capital Y by partial epsilon, and after differentiating putting epsilon 0, and that is ciyi. So that is eta I, and in this case the x is not changing, so x is not changing mean capital X is equal to the small x. So if we differentiate capital X with epsilon, that is 0, given epsilon 0, so that is xi. So that means the symmetry generator in this case take the form xi, which is 0, so that is partial by partial x part is 0, and eta is ciyi partial by partial y. So this is the symmetry generator. How many parameters are there? Let's expand it. This generator can be written c1 y1 c2 y2 up to cn yn partial by partial y. So there are in generator x1 is y1 partial by partial y, x2 is y2 partial by partial y, x3 is y3 partial by partial y, and so on. Xn is a yn partial by partial y. So we have the algebra for the homogeneous equation. We have these in Lie symmetry generators for the homogeneous for the equation a n y n minus 1 yn minus 1 a not y equal to 0. So there are this conclude the conclusion there are at least n Lie symmetries for nth order ODEs. So this is the minimum value. There will be more than n Lie symmetries for some nth order linear differential equation, and these symmetries correspond to all the solution of the fundamental set. So if we have a linear order differential equation, if we have a linear ODE of order n, then there will be at least n symmetries. For example, if we have a second order, let's say xy double dash plus some y dash and plus some x square y equal to, let's say, sin x. So this is second order. So it is confirmed that it admit at least two symmetries. Similarly, if the order is 3, then we are sure that there must be 3 Lie symmetries. So that's all about this concept that linear nth order ODE will admit at least n Lie symmetries, and each symmetry correspond to the one member of the fundamental set of solutions. So that is the conclusion of this lecture. Thank you.